Picture this. Your app is running great on 5 containers. Traffic doubles. You add 10 more containers manually. Now one crashes at 2 a.m. Another runs out of memory. 2 are sitting idle doing nothing while the others are overwhelmed. Managing containers at scale manually is chaos. And that's exactly the problem Kubernetes was invented to solve. Kubernetes is a container orchestrator. You tell it what you want: run 10 copies of my app, always keep them healthy, spread them across machines, and Kubernetes makes it happen automatically. If a container crashes, Kubernetes restarts it. If traffic spikes, it scales up. If a server dies, it moves the containers to healthy machines. Think of Kubernetes as the operating system for your entire container fleet. You stop thinking about individual containers and start thinking about desired state. Here's where it gets interesting. Running Kubernetes yourself means managing 2 layers, the control plane and the worker nodes. The control plane is the brain. It schedules containers, tracks cluster state, and handles all the orchestration logic. Running it reliably is genuinely complex. AKS takes the control plane completely off your hands. Microsoft runs it, patches it, and guarantees its availability for free. You pay only for the worker node VMs where your containers actually run. This is a huge deal. Setting up a production-ready Kubernetes control plane from scratch can take days. With AKS, it takes one CLI command and about 5 minutes. And because AKS is a native Azure service, it integrates directly with Azure Active Directory for authentication, Azure Monitor for observability, Container Registry for private images, and Key Vault for secrets. Everything connects without custom wiring. Before you deploy anything, you need to understand 4 concepts. Don't worry, these are simpler than they sound. A node is just a virtual machine. Your cluster has a pool of nodes, and Kubernetes decides which node runs which container. A pod is the smallest thing Kubernetes manages. It wraps 1 or more containers that share a network address and storage. Most of the time, 1 pod equals 1 container. A deployment is how you tell Kubernetes what to run. You say, I want 5 copies of this container image, always. Kubernetes creates 5 pods and keeps exactly 5 running at all times. If one dies, it creates a replacement immediately. A service is the stable network entry point. Pods are temporary, they get created and destroyed constantly. A service provides a fixed IP and DNS name that always routes to healthy pods, no matter how many times they restart. Now here's the important part: actually deploying something. First, connect your kubectl CLI to your AKS cluster with AKS get credentials. This downloads the cluster credentials to your local kubeconfig file. Then you write a deployment YAML file. It's a simple text file that says, use this container image, run 3 replicas, give each container half a CPU and 512 megabytes of memory. That's it. Run kubectl apply fdeployment.yaml and Kubernetes schedules your pods across the cluster nodes within seconds. Use kubectl get pods to see them running. Use kubectl logs followed by the pod name to see stout output, exactly like Docker logs. Use kubectl describe pod to investigate if something isn't starting correctly. Most developers get comfortable with these 4 commands in their first hour, and they cover 80% of day-to-day Kubernetes work. Here's where most beginners get confused, and once you understand this, everything clicks. You have 3 ways to expose your application. Cluster IP is internal only, other pods inside the cluster can reach it, but nothing outside can. Use this for databases and internal microservices. Load balancer creates a real Azure load balancer with a public IP. External traffic hits the load balancer and gets routed to your pods. Simple and effective for a single service. But here's where it gets interesting. When you have 10 different services and you want to expose them all under one domain with path-based routing, /API goes here, /frontend goes there, you use Ingress. One Ingress controller handles TLS termination and routes all incoming HTTP traffic to the right service based on rules you define. This pattern is how most production AKS setups work. Most people set up Kubernetes and forget about scaling. Then traffic spikes and their app falls over. Don't make that mistake. The horizontal pod autoscaler HPA watches your pod's CPU usage. When it crosses your threshold, it adds more pods automatically. When load drops, it removes them. You set the minimum replicas, maximum replicas, and target CPU percentage. Kubernetes does the rest. But here's the catch: if all your nodes are full, new pods have nowhere to run. That's where Cluster Autoscaler comes in. It watches for pods stuck in pending state and adds a new node to the cluster automatically. When load drops and nodes are underused, it removes them to save cost. For event-driven workloads, Kata takes this further. It can scale pods based on queue depth, message count, or HTTP traffic rate, and scale all the way down to 0 when there's nothing to process. Containers are stateless by design. When a pod restarts, everything written to its local file system disappears. For databases and file storage, you need persistent volumes. AKS integrates with two Azure storage types. Azure Managed Disks or Fast Block Storage, think of them like a hard drive attached to your pod. They give you great performance for databases like PostgreSQL or MongoDB running inside Kubernetes. The trade-off is that a disk can only be attached to one pod at a time. Azure Files uses the SMB protocol and can be mounted by multiple pods simultaneously. Use it when several pods need to read and write shared files, a media processing pipeline, for example, where multiple workers process files from the same directory. In Kubernetes, you define a persistent volume claim, essentially a request for storage of a certain size and type, and AKS automatically provisions the Azure disk or file share behind it. Security is where most teams underinvest in Kubernetes. Here's what actually matters. Kubernetes RBAC controls what users and service accounts can do inside the cluster, who can deploy, who can read secrets, who can delete pods. Without RBAC configured properly, any authenticated user has full cluster access. Integrate AKS with Azure Active Directory so your team logs in with their corporate identity. No separate Kubernetes usernames and passwords to manage. When someone leaves the organization, revoking their Azure AD account revokes their cluster access automatically. For your pods accessing Azure services, Key Vault, storage, SQL database, use workload identity. This assigns a managed identity to specific pods so they authenticate to Azure services without any credentials stored in environment variables or Kubernetes secrets. Finally, for production, create a private cluster where the API server has no public IP, it's only reachable from within your VNet. Deploying to AKS manually gets old fast. Here's how to automate it properly. A GitHub Actions workflow does three things on every push to main. First, it builds your Docker image and tags it with the git commit SHA. Never use latest as a tag in production. Second, it pushes the image to Azure Container Registry. Third, it updates the image reference in your Kubernetes deployment and applies it with kubectl. The Azure/AKS set context action handles authentication between your workflow and the cluster using a service principal or managed identity, no credentials hard-coded in the workflow. Kubernetes performs rolling updates by default. It replaces pods one at a time, waiting for each new pod to pass its health check before replacing the next. Your users see zero downtime during the deployment. And if something goes wrong? One command, kubectl rollout undo, instantly switches back to the previous version. You've deployed your app, it's scaling, it's secure. Now, can you see what's happening inside the cluster? Enable container insights when you create your AKS cluster. It automatically collects CPU and memory metrics for every node and pod, streams container logs to log analytics, and gives you a live view of cluster health in the Azure portal. The metrics that matter most in production: node CPU percentage. If nodes stay above 80%, you need more capacity. Pod restart count. Any unexpected restart is a bug worth investigating. Pending pods. Pods stuck in pending state mean your cluster doesn't have enough resources to schedule them. Set alerts on these three. They will catch 90% of production problems before your users report them. To summarize this video, AKS gives you production-grade Kubernetes with Microsoft managing the hard parts. You focus on deploying, scaling, and monitoring your applications, not on keeping the cluster itself alive. That's the whole point. Think through what's happening. The horizontal pod autoscaler did its job. It saw CPU above the threshold and created new pods. But those pods are pending, which means they can't be scheduled. The scheduler can't find a node with enough available CPU and memory to place them. This happens when all your existing nodes are full. HPA scales pods, but it can't create new VMs. That's a completely separate concern. Cluster Autoscaler solves this. It watches for pods stuck in pending state due to insufficient node resources. When it detects them, it provisions a new node from your node pool, adds it to the cluster, and the scheduler immediately places the pending pods on it. Enable Cluster Autoscaler when you create your node pool, and set a minimum and maximum node count. AKS handles the rest, scaling nodes up under load and back down during quiet periods to save cost. Active Recall, HPA scales pods. Cluster Autoscaler scales nodes. You need both for a fully elastic AKS cluster.